We now want to talk about abstract classes and the so-called concept of interfaces. This is a relatively short section as a preparation for C++, which will implement all this functionality, and the relationship with the introduction we give to conceptual hierarchies. Now, the abstract classes is by definition classes which have no instances. You cannot create an object of an abstract class. So if I ask you to give me an object of a transaction, for example, it's too general. Or given an example of an animal or a finite difference method, it's too generic. So they have no instances. And going back to the previous sections, the abstract classes correspond to this superordinate concepts. So there's a very high level of abstraction, very difficult to find the attributes. So the if you found your concept hierarchies when you're modeling your application, you know that the superordinate concepts will be mapped to abstract classes. And so the abstract classes have no body. The body is actually given by the basic concepts, which are one level deeper than the abstract classes. So let me draw the diagram again. So here is the superordinate level. Here is the basic level, which everybody understands. So the basic level is derived, as it were, from the superordinate level. So the superordinate level is very abstract, and this corresponds to my ABC. What do I mean ABC? Abstract base class. So the superordinate level does have functions and so on, but they're all abstract functions. And the basic level implements the abstract functions here, so it gives a body to the actual functions. So this is a pattern, and we'll see discovering this hierarchy is very good because of the following reason. We'll talk about client software. Here we have a client piece of software which talks to the superordinate object at runtime, the base class reference or pointer, but at runtime it's pointing to some base class, some derived class. So it could be a B1 class or a B2 class. So here's my base class. So the client only gets a pointer to an abstract base class, which at runtime can be a B1 or a B2 class, but it's got no idea of what's going on, which is great because I can change my application. I can create a new class B3, and the client is still talking to S at runtime. Somebody else has to initialize and make the link between S and B1 and B2 and so on. But this is the basic idea behind polymorphism, what we will discuss in the next sections. Okay, so to summarize, an abstract class, you cannot create instances or objects of abstract classes because they're too generic. As I've said, this is the superordinate level in the conceptual hierarchy, and the basic classes actually do the actual work. Okay, so why do we want abstract base classes? It's a placeholder. It's the base class is the root, as it were, for a hierarchy of more specific classes. So the client code, I just mentioned it, the client code uses the abstract base class in functions, but the abstract base class refers to a derived class at runtime. So in other words, the client does not know need to know about derived classes, and the substitutability principle is the following. I could have a, let me go back to my pen here. I could have a function which accepts a const reference to a base class. So you know what const references are from the previous set of slides, and my client just talks to the base class reference at runtime. But somewhere along the line, by somebody else, the actual link is made between the base class reference and its derived class. So that's and I can change B1 to B2. So anywhere I have a function which accepts a base class reference as an input argument, I can call the actual function with a derived class, and that's very powerful. And the derived class could be future derived classes. So let's say you've created a nice application, and your client is impervious to the changes here. So it might be like to price a function or something. So these could be options. B1 and B2 you've created, but the client says to you, I'd like a new one, B3. So there's a new class here. What you do is you create the new class, B3, with all the necessary functions, which we'll talk about later, and off you go. You just make the link between S and B3 and you're finished. Normally there's another object here, another piece of code. I draw it as a person. It's a factory. So these are factories. So somebody builds all the stuff for you, and we see later how it actually works. So the client, here's a factory, factory. So the client actually talks to the it gets a base class at runtime, but underwater, let's say, he's talking to one of these objects here. So if something changes here, your client does not have to change, which is very powerful. This is the so-called substitutability principle. Let's take a very simple example now. Payoffs, fairly fundamental in option pricing. This is UML, Unified Modeling Language. It's a nice representation of classes, much nicer than the squeaky scrawly stuff I wrote here. Okay, so the base class is abstract. So payoff, you cannot create a payoff. It's too generic. It's a superordinate level. But you can create a call payoff and a bull spread payoff and a put payoff and so on. So ... means etc. etc. So this is the hierarchy. So going back to the original conceptual levels, this is the superordinate level, you might say, and here's the basic level. Okay. So we now have to look at the functions in each class. So to make a long story short, we'll talk about it when we get to the C++ part. My class payoff has a virtual function. You'll see why. It's got a payoff, so it's got a double S, so it's a one-factor model. So S is your underlying stock, for example, and it's pure virtual. It's a const because it does not change the member data. It returns a double and it's virtual. We'll see in a moment why it's needed for the principle of substitutability. And it's equal to 0. What do I mean 0? It makes it pure virtual. It's got no body. It may not have a body. So it has to be this is what makes the class abstract. Because if you try to create an object of payoff, you say sorry, it's abstract because one of its functions is abstract. The derived classes, here's a typical example. A call payoff is derived from payoff, it's inheritance. So basically when I say call payoff is public payoff, he's actually implementing the relationship here between the call payoff and the payoff. Okay, of course you know that in order to price, you know what the payoff is, it's max S minus K and 0. So we need a strike price. So in the constructor, we got a default constructor as well. It's not so interesting, but you got a constructor with a strike price as input. So in the body of the class of the constructor, you have to initialize K, of course. So my payoff will be here's my specification. So you know that the payoff would be just the max of S minus K. So this is an example of abstract classes and their implementation, and you'll always see it in much more detail actually for finite difference hierarchies. We will have here, we will have partial differential equation hierarchies, instrument hierarchies, and so on. So this is very important. So it's a bit of a forward reference because we haven't really discussed what virtual functions are, pedagogically speaking. Okay, so the last remark in the course is to talk about interfaces. What is an interface? Now, an interface is just a specification of a bunch of pure functions, like the pure virtual functions here. So it's really it corresponds to the superordinate level. It's all the functions in the superordinate level, and the functions have no body, and the interface has no data and no non-abstract functions. And so the unfortunate thing about C++ is that it does not support interfaces. There's no keyword interface. In some other language you do it. You can do it, like Java and C#. We simulate it with a minimum abstract base class. What do I mean a minimum abstract base class? An abstract base class which has no member data and only pure virtual member functions. And we see many more examples later on. So that's more or less the introduction to abstract classes and interfaces. So it's a link. This section was the link between the conceptual hierarchies we talked about and the actual implementation in C++ of these abstract classes. So abstract classes are useful to have because of the so-called substitutability principle, which we will repeat in a moment as well. Okay, so we'll take a break here now and see you later.